So, how exactly do you give an AI a flawless, up to date memory without having to completely retrain it? Think about it. Standard large language models are absolutely brilliant, but they have this one huge fatal flaw. Their knowledge is entirely frozen in time the exact second they finish training. And, as we all know, they have a pretty notorious habit of just hallucinating facts when they don't know the answer. Well, if you've ever wondered how major enterprise systems actually solve this problem, you are in exactly the right place. In today's explainer, we're going to solve this by building what is essentially an information factory. Welcome to our explainer on RAG systems. Whether you're a total beginner just trying to wrap your head around how this architecture actually works, or maybe you're a practitioner looking to totally master your technical interviews and level up to production-grade design, we are going to build some really deep technical intuition today. Okay, here is our quick roadmap for today. We'll start with number 1. What is RAG? Then 2, the end-to-end architecture. 3, building the knowledge base. 4, retrieval and grounded generation. And finally, number 5, evaluation and production mastery. Let's jump right into section 1. What is RAG? To really get this, I want you to imagine a brilliant consultant. They write beautifully, they communicate perfectly, but they haven't read a single one of your company's internal policies. A standard language model is exactly like that consultant, just trying to answer off the top of their head from general memory. But a RAG system, it totally changes the game. It first sends that consultant over to a librarian, grabs the absolute most relevant pages, slams those pages down on the desk, and demands an answer supported strictly by what's on that paper. And that gives us our formal definition, Retrieval Augmented Generation, or RAG. It's essentially a grounding architecture. By forcing the AI model to rely on supplied external evidence, we drastically reduce those crazy hallucinations. Plus, just updating a search index is vastly cheaper and way faster than trying to retrain a massive AI model from scratch every time your data changes. Moving right along to section 2, the end-to-end architecture. A full RAG system actually consists of 2 very distinct pipelines, and this is crucial to understand. Steps 1 and 2, ingesting and indexing your data, those happen completely offline. Meanwhile, steps 3 and 4, retrieving and generation, those happen online, basically at the exact split second a user asks a question. Interestingly enough, in technical interviews, candidates often mistakenly only talk about the online pipeline, but a true production-ready answer absolutely must cover both. Which brings us to section 3, building the knowledge base. Okay, I need to share an absolute golden rule for production with you. Never, ever index content without a deterministic source identity and permission metadata. Literally, just don't do it. Without knowing exactly where a piece of text came from, and more importantly, who is actually allowed to see it, your citations, your content updates, and your security filtering are going to become totally unreliable. So, once you have your documents securely ingested, you need to divide them up into retrievable units. And this brings up a super common, high-stakes interview question. How do you choose the right chunk size for your documents? It sounds so simple, right? But it truly tests a developer's design judgment. The reality is, there is no universal best size. Using a fixed token size is super simple, sure, but you risk slicing a crucial sentence right in half. Structure-aware chunking is awesome because it respects natural paragraphs, which is absolutely perfect for things like contracts or code, but it requires some really complex parsers. Then you got semantic chunking. It's great for long narratives, but it can be pretty costly and unpredictable. A truly strong engineer establishes a baseline based on the actual structure of the documents and then actively tests it to maximize quality while keeping latency as low as possible. Now, once everything is chunked, we essentially have 2 main ways to search that index. Sparse retrieval, like BM25, looks for exact keywords. It is absolutely fantastic for finding rare names or specific product IDs. Dense retrieval, which you probably know as vector search, looks for mathematical similarity in meaning. It's basically magic for handling paraphrases or vague concepts. Modern production systems almost always use a hybrid approach so they can capture the absolute best of both worlds. Let's shift gears to section 4, retrieval and grounded generation. Let's be honest for a second. Users are messy. They ask incredibly vague, context-dependent questions. So before we even search, the system has to clean up that request using query understanding. This means rewriting vague questions into standalone searches, extracting specific entities like dates, and applying those metadata filters we talked about so a user only searches what they actually have permission to view. This step is absolutely crucial for building a highly effective retrieval plan. Now, because hybrid retrieval uses totally different scoring scales, you've got keyword scores over here and vector math over there, you can't just casually add them together. We have to use algorithms like reciprocal rank fusion. And hey, you do not need to memorize the math here. Just grasp the core concept. It safely merges rankings from totally different methods by looking at their rank positions rather than their raw incompatible scores. To squeeze out maximum accuracy, we use a two-step funnel. The first stage retrieval fetches a really broad set of candidates super quickly. Then, a re-ranker, usually something like a cross-encoder model, steps in. It jointly reads the user's query and each candidate document to heavily scrutinize the relevance. We retrieve broadly at first so we don't accidentally miss anything, but we only re-rank a very small batch because running those complex models is computationally expensive. Finally, we build the prompt for the generator. We supply strict system rules, we feed in our cited evidence, and we drop in the user's question. But crucially, you absolutely must require abstention. A trustworthy RAG system has to know exactly when to say, I don't know. If the provided context simply doesn't contain the facts, it needs to stop right there. That brings us to our final section, number 5, evaluation and production mastery. A mature engineering team measures retrieval and generation entirely separately. Take a close look at the difference between answer relevance and faithfulness here. An answer can be totally relevant to what the user asked, but completely unfaithful to the source documents, which basically means it just hallucinated a really good-sounding answer. Always remember this. An absolutely excellent, world-class LLM cannot magically recover evidence that your retrieval system failed to find in the first place. So when things inevitably go wrong, how do you diagnose it? Well, there's a brilliant diagnostic cheat code called the Oracle Context Test. If your system gives a bad answer, manually give the generator the known 100% correct evidence. If it still fails, you know your LLM prompting is the problem. But if it succeeds, the problem is upstream somewhere in your retrieval pipeline. It's a perfect way to isolate exactly which stage is broken. This actually leads us right into a major architectural choice that trips a lot of people up: RAG versus fine-tuning. When do you actually use which? Well, RAG is perfectly designed to provide fresh, private, factual knowledge. Fine-tuning, on the other hand, is used to shape the behavior, the tone, and the format of the model's output. Fine-tuning is actually a really terrible mechanism for trying to store frequently changing factual memory. They are complementary tools, not competitors. Before we wrap up today, we really have to talk about security. Production systems face massive real-world risks like prompt injections hidden straight inside uploaded documents or broken access controls leaking sensitive data. The absolute golden rule here is that authorization must be enforced by deterministic, hard-coded application logic before retrieval even happens. You filter out unauthorized documents before the search is even executed. You never, ever just delegate your security to the LLM. We've covered the complete end-to-end architecture today, going all the way from messy PDFs to perfectly grounded, secure answers. But I want to leave you with this final, provocative thought. If you actually deployed this system tomorrow, how exactly would you handle a sudden, massive quality regression? Or how would you scale up your chunking and vector search to handle 10 million documents while keeping your user latency under a single second? Think deeply about the frameworks we discussed today, because honestly, that is where the real engineering begins. Keep exploring, keep building, and thank you so much for joining me on this explainer.